Hey friends, Dr. Borole is here. Today we are going to discuss the temperature sensors and transducers. The temperature sensors are the sensors which can be used for sensing the temperature of a object or atmosphere and provides the output which is proportional to the temperature. This output is probably in terms of voltage or current. The temperature sensors principle of operation is based on the heating and cooling effect of temperature on various materials, most commonly the metals. The change in temperature may leads to the physical change or chemical state change of the substance. The second principle may be change in temperature may results to change in physical dimensions, particularly used in thermometers. The third principle is change in temperature results to change in some of the electrical properties of the material, like resistance of the metallic wires. Another principle is some of the material generates the EMF when they are subjected to change in temperature. For example, a PN junction made with semiconductors. The fifth principle is the temperature change gives rise to intensity of radiation emitted from the material. Based on these five principles, there are various temperature sensors and detectors exist in the market. Commonly used electrical methods for detection of the temperature are listed as follows. When temperature of a material changes, it probably gives rise to change in resistance. So electrically, detection of change in resistance gives detection of temperature. Detection of thermo EMFs. Some material generates the EMF which is proportional to the temperature change. If we detect this thermal EMF, we can able to measure the change in temperature. The third commonly used method is detection of radiations. Normally, the temperature source radiates the thermal radiations. These radiations can be detected by using pyrometric sensors, and the temperature can be matched by matching the radiation intensities. These type of measurements are done for very high temperature measurement. Let us see the first type of detection method on which the resistance type of temperature sensor is based, called RTD, resistance temperature detector. In RTD, the resistance of a metal wire is change proportional to temperature. In metals particularly, if the temperature is increased, the resistance of the material is increasing. Thus, most of the metals have positive temperature coefficient of resistance. The temperature coefficient is defined as change in resistance with respect to change in temperature. Since in the metals, the resistance of a metal wire which is subjected to temperature changes its resistance. The resistance is increased with change in temperature, and therefore the temperature coefficient of metals is positive. In semiconductors particularly, if the temperature is increased, the resistivity of a semiconductor bar will decrease. So delta R by delta T, that is the temperature coefficient, is negative in case of semiconductors. The temperature measurement sensors are based on use of metal wires or use of semiconductors for RTDs. In metals, the relation between temperature and resistance is quite popular and studied earlier in the 12th class also. The following equation gives the change in resistance of the metal wire with respect to change in temperature. RT is equal to R0 into bracket 1 plus alpha T plus beta T square plus C T raised to 3 and so on. So basically it is a non-linear quadratic relationship, whereas the coefficients alpha, beta or A, B and C are diminishing. Means A is the largest coefficient, B, C, D onwards are very low, and therefore the temp resistance RT, that is the resistance at temperature T, is approximately given as R0 into 1 plus alpha 0 T or A 0 T, and that is equal to RT1 into bracket 1 plus alpha 1 into T, where RT1 is the resistance at temperature T1, whereas R0 is the resistance at temperature 0 degree centigrade. So this relationship tells us that the resistance of a material at T degree centigrade, that is RT, is R0 into bracket 1 plus alpha 0 T, where R0 is the temperature at 0 degree centigrade. In this equation, you can replace R0 by RT1 also. So reference can be taken as 0 degree centigrade or reference can be taken as T1 degree centigrade. Whereas alpha is a temperature coefficient. From this expression, the alpha is defined as alpha is equal to RT minus RT1 divided by RT1 into delta T, that is T minus T1. If you are using 0 degree as a reference, then RT1 will be replaced by R0. The same thing is defined here. Okay. For a well-known temperature RTD sensor PT100, alpha 0 is approximately coming out to be 0.00391 per degree centigrade. It means that for every degree change in temperature, the resistance will be changed by 3.91 milliohm. The characteristic of RTD is shown here. This is the curve, resistance of RTD versus temperature. Now, if you see here at 0 degrees centigrade, the sensor RTD PT100 is having 100 ohm resistance. And if the temperature changes linearly, the change in resistance is also mostly linear. The resistance for various temperature values is listed here on y-axis. From this curve, you can find out the resistance of RTD at any temperature. For example, at 400 degrees centigrade, if you see here, at 400 degrees centigrade, the resistance value is 250 ohm. And this curve is plotted by using this expression. RT is equal to R0 into bracket 1 plus alpha 0 T, where alpha 0 is 0.00391 ohm per degree centigrade. The various material those are used for preparation of RTD sensors are shown here in the table. For example, for copper, the temperature range is from minus 200 to 260 degrees centigrade and alpha value is shown 0.00427 per degree centigrade. Copper is a cheap material and therefore this is low cost RTD. Another material used is molybdenum, which is capable of providing the range from minus 200 to 200 degrees centigrade measurement. Nickel can also be used for preparation of RTDs and which provides the measurement range from minus 80 degrees centigrade to 260 degrees centigrade, having somewhat larger alpha. The platinum RTDs are very common and they are offering the measurement range from minus 240 degrees centigrade to 660 degrees centigrade. The RTDs are available in various tolerance classes from class A to class D, and the temperature tolerance is shown here. It can provide the tolerance of plus minus 0.15 plus 0.002 into T. This is the tolerance in the resistance value that is shown. The various configurations for RTDs are shown here. RTD is a simple resistive element made from the specific material. So it has two wires for connection. So two wire RTD consists of two wires only, and this RTD is normally subjected to the point where the temperature is to be measured. Sometimes three wire configuration of the sensor is also available, like this shown in the figure. Whereas 4-wire RTD configurations are also available. They can have dual wire connected to both the ends. These multiple wires are used to compensate the lead resistance. Platinum is most commonly used material because it is having very high accuracy and reproducibility. And mostly the platinum resistance thermometer, those are linear. You can see the graph of PT100, whatever shown earlier also. At 0 degrees centigrade, PT100 sensor is having the resistance R0 of 100 ohm and it linearly increases with temperature. From 0 to 100 degree, the change in resistance will be from R0 to R100. And it is shown by a approximate straight line that is governed by the equation R0 into 1 plus alpha 0 T, where alpha 0 is the temperature coefficient. Now see the construction of RTD. RTD is a simple resistance wire. It consists of a insulating former, mostly the mica former, which is electrically insulating, and on which the platinum wire is wound, and two ends of the platinum wires are taken out, and this is the sensor. Whenever this sensor is subjected to temperature, the resistance of the platinum wire changes as discussed above, and that change in resistance can be further measured by the electronic circuit. Typical construction wound sensor is shown here. On a circular former, cylindrical former, the wire is wound and leads are taken out. Another construction is a coil type of element. It consists of a coil wound on a former with multiple former elements, and the total resistance will be the resistance of a total wire, with the leads are connected to the extreme ends of the platinum wire, which is shown in this figure. A thin film type of RTD is shown, in which on a ceramic substance the platinum wire will be monolithically fabricated by the electronic fabrications process, and this way the wire will be just like a printing wire will be printed on the ceramic surface, and two ends of the wire are connected to the leads. Whenever this sensing wire is subjected to temperature change, its resistance will be changed, and that change in resistance is proportional to change in temperature. The sensor physically look like as shown in the figure 2. So these sensors are insulated by using a electrical insulator and inserted in a metallic tube, and the sensor will be present at the tip of this metallic tube. The metallic tube provides the strength to the sensor so that it can be installed in the process installation. The arrangement for installation by using this crude nut and bolt arrangement is shown, so that the sensor can be installed on the equipment where the temperature is to be measured. The elements we have seen, the wire wound element, coil type of element, and thin film type of elements, these elements are properly inserted inside this thermally conducting metallic tube, so that it can appropriately sense the temperature, and the leads are taken out for electrical circuit connection. The semiconductor materials are also used for thermistors. The measurement of this change in resistance we have seen can be converted to appropriate electrical voltage by using a simple technique of Wheatstone Bridge. See here, the Wheatstone Bridge with four arms are shown. Out of these four arms, one of the arm will be replaced by a sensor whose resistance is not known. And we know Wheatstone Bridge can be used for measurement of unknown resistance in terms of the other branch resistance values. The output of the Wheatstone Bridge is connected to an amplifier, that is VAB, that is connected to the amplifier, and this amplifier is a differential amplifier. The output of this amplifier is gain of the amplifier into the input differential voltage VAB. We can find out what is the output voltage that is generated by this Wheatstone bridge when there is a change in resistance of RTD. Let us apply the principle of voltage division theorem to the bridge circuit arms using R1 and R3. So therefore voltage at A with respect to the common point is VA, that is equal to R3 upon R1 plus R3 into Vs. Similarly, voltage at point B is given by RT, that is the resistance of RTD, upon total resistance R2 plus RT into the supply voltage Vs. So we got the voltage VA and VB. Please note here that the voltage divider theorem is already studied in the previous classes, and it is very simple based on the Kirchhoff's voltage law that is applied to the loop. In this expression, if R1 is equal to R2 is equal to R3 is equal to R0 is say R, then substituting these values in the above expression gives you R upon twice R into Vs as Va. Vb is equal to RT upon R plus RT into Vs. If RT is R plus delta R, what it means? The resistance at T degree centigrade is changed from the resistance R by the amount delta R. Therefore, we can replace RT by R plus delta R. Therefore, VO is equal to VB minus VA as Vs in bracket R plus delta R upon R plus delta R minus R by 2R. Simplifying this expression further, so here VO is equal to, take R common from numerator and denominator and cancel it. It comes out to be 1 plus delta R by R upon 2 plus delta R by R minus 1 by 2. In the denominator, this term delta R by R is very small compared to 2, and therefore it can be ignored. And therefore the output voltage VO will be approximately 1 plus delta R by R upon 2 minus 1 half. Take 1 half common and simplify the expression. You will get VO is equal to Vs by 2 into delta R by R. This equation indicates that the output voltage of a Wien bridge circuit is proportional to the change in resistance, which is in turn proportional to change in temperature. It is also proportional to the supply voltage amplitude. Larger the supply voltage, larger will be the output voltage, and the sensitivity can be increased by increasing the supply voltage. So this way, we have converted the change in resistance due to temperature in the RTD to the proportional change in output voltage, which is amplified further by the amplifier circuit by gain AV, and the output voltage VO is available. This output can be further given to the processing circuit or display circuit to display the temperature. The advantages of RTDs are as follows. It can be used for wide temperature measurement range from minus 200 degrees centigrade to 650 degrees centigrade. The RTD is having very high accuracy, particularly the platinum resistance thermometer is very common in practice. It is good and quite quick dynamic response available with RTD. RTD have good linearity over the small range of operation. There is no need of temperature compensation while using RTD, which is essential while using the another temperature sensor like thermocouple. The disadvantages of RTDs are they are larger in size and they are costly compared to other sensors. They have good resolution and accuracy. This is basically a advantage. The another disadvantage is that it needs the external biasing power supply to convert the change in resistance to the proportional voltage. RTD is basically a passive sensor which needs the external supply and the additional Wheatstone Bridge circuit to convert the change in resistance due to temperature into proportional voltage. Another type of temperature sensor is thermistor. The thermistors are made with the semiconductor material and they are having negative temperature coefficient of resistance. They can be made up of doped ceramic plus metal oxides also. These ceramics doped with metal oxides thermistors can have positive temperature coefficients, whereas basic semiconductor material thermistors have negative temperature coefficient of resistance. Normally, a sintered mixture of sulfide, selenide, and oxides of manganese, nickel, cobalt, iron, and copper, etc., can be used for development of thermistor sensors. The negative temperature coefficient (E&TC) means when the temperature of a thermistor device is increased or decreased, the resistance of thermistor will decrease or increase respectively. The positive temperature coefficient (PTC) is nothing but when temperature of the thermistor increases, the resistance is increases. Whereas when the temperature decreases, the resistance decreases. That is called positive temperature coefficient. So change in the resistance due to temperature is positive here, whereas in negative temperature coefficient thermistor, the change in resistance due to change in temperature is negative. A typical thermistors are shown in this figure. The thermistor consists of a glass coating. Inside it, there is a bead. Bead means a piece of semiconductor material with the ends are taken out for the connection. Probe type of thermo sensors or thermistor sensors is shown here consists of a small bead here inside and which is enclosed in the glass enclosure and the two wires are taken out. Whereas the rod type of thermistor is shown here where these two ends are connected to the external wire. It's a simple semiconductor bar or it can be a disc of semiconductor or it can be a rod of semiconductor to which the metal wires are connected. Physically, the thermistors look like shown in the figure. This is the disc type of semiconductor. This is a rod type of semiconductor thermistor. Whereas the basic semiconductor wafer is enclosed inside a conducting body that is mostly a metallic body so that when the temperature of a particular object to be measured, this thermistor will be firmly connected to the body of or surface of that object, and thermistor resistance will be decided by the temperature at the point of contact. The value of the resistance of the thermistor with respect to temperature is given by RT is equal to, means the resistance at T degree centigrade is given by R0 into e raised to beta in bracket 1 by T minus 1 by T0, whereas R0 is the resistance at 0 degree Kelvin, R0 is the resistance at T 0 degree Kelvin, and RT is the resistance at T degree Kelvin, and beta is the coefficient of temperature. The international standard symbol is shown in the first figure, whereas American standard symbol of a thermistor is shown here. The characteristics of the thermistors are shown here. On y-axis there is a change in resistance in kilo ohm, and on x-axis there is change in temperature. And you will see that the resistance increases here with change in temperature. This particular thermistor is having positive temperature coefficient of resistance. Whereas in the second curve, the resistance decreases with increase in temperature. This particularly is a sensor with semiconductor material which is having negative temperature coefficient. And both the curve, you will see that the change in resistance is slightly non-linear function of change in temperature. And therefore, thermistors are normally used for very short range of measurement or detection of a temperature at particular point only. They are not used for linear measurements. They are normally used for protection against very high temperature and very low temperature by detecting the 2 point temperature for protections. The measurement of temperature using thermistor is shown in the following figure. In this circuit, again we are using the Wheatstone Bridge circuit, and we will replace one of the arm of the Wheatstone Bridge circuit by using thermistor. The output of the Wheatstone Bridge circuit is taken between point A and point B, that is called as VAB, and we have derived the expression for the output of Wheatstone Bridge circuit. VAB here will be decided by the resistance of the thermistor. If the thermistor resistance is decreased, the VA value will be increased, whereas VB value remains constant because R1 and R2 are constant, and therefore VAB will increase when the resistance of the thermistor is decreasing, and vice versa. When the thermistor resistance value is increasing, the value of voltage at A will decrease. The reference is the voltage divider theorem. Therefore, when VA decreases, VAB decreases if the resistance of the thermistor is increasing. This VAB will be further amplified by the amplifier, and output voltage of the amplifier is available for further processing. The temperature range of the thermistor sensor is normally low compared to RTD, that is from minus 100 degree centigrade to 300 degree centigrade, and accuracy will be 0.05 degree centigrade to 1.5 degree centigrade. The advantages of thermistors are precision temperature measurement is possible using thermistor because it is very sensitive to the temperature changes, but it is non-linear. They are highly accurate also. The accuracy is in the range of 0.05 degree centigrade to 1.5 degree centigrade. The disadvantages of thermistors are the characteristics of the thermistors are very non-linear and therefore they are not suitable for wide linear range of application. They are therefore suitable for the temperature measurement. Therefore, they are suitable for measurement of single temperature detection or two-point temperature detection. The application of thermistors are typically in fridge and refrigerators as a thermostat. In cookers and deep fryers, they can be used to control the temperature around the set value. In washing machine and dishwasher also, they can be used to control the temperature of the water. At a particular point, they can turn on the heater if the temperature goes below the set value, and if the temperature goes above the set value, they will be turned off the heater. In a central heating system or centralized AC system, normally thermostats are used for detecting the environmental temperature in that atmosphere, and when the temperature reaches to the set value, the system will be cut off so that temperature will be controlled. In the industrial process control system also, the thermistors can be used for detection of single temperature. Heating and ventilation system automatic control also utilizes thermistors. Air conditioning, fire alarm systems can also utilize thermistors. Thermal protection in batteries and charging system also utilizes local thermistors to monitor the temperature of a battery. When the temperature exceeds a safe temperature value, the thermistor will generate the signal and which will be handled by the further protection circuitry to turn off the charging of the batteries nowadays. Sometimes in your examination there will be question as shown in the example. A thermistor has a material constant beta of 300 degree Kelvin and its resistance is 105 kilo ohm at 300 degree Kelvin. What will be the resistance of the thermistor at 600 degree Kelvin? So as usual, first read the statement and note down what is given. The beta value is given 3000 degree Kelvin. The resistance at 300 degree Kelvin is given as 105 kilo ohm. And what is to be calculated is the resistance at 600 degree Kelvin. We have the expression RT is equal to R0 into e raised to beta in bracket 1 by T minus 1 by T0. Substitute the values. RT given at 300 degree Kelvin is 105 kilo ohm. That is 105 into 10 raised to 3 ohm. Whereas beta given is 3000. Temperature at which the resistance is to be measured is 600, that is R600. So therefore T is 600, so 1 by 600 here minus the given temperature, the given resistance at 300 degree is T1, therefore 1 by 300 here. And therefore simplify the expression, you will get the resistance at 600 degree Kelvin is 707.49 ohm. So resistance is drastically changed from 105 kilo ohm to 707.49 ohm in 300 degree Kelvin, from 300 degree Kelvin to 600 degree Kelvin. The difference will be 300 degree Kelvin. That is nothing but from 27 degrees centigrade to 327 degrees centigrade. The another sensors which can be used for temperature measurement is called as thermocouple. Today we will stop here, friends. We will see the thermocouple sensors in the next lecture. Till then, bye bye.